Welcome, ladies and gentlemen. This is the first lecture of the course in Advanced Electromagnetism, or whatever the name of the course. Perhaps you have noticed that I am not the lecturer. This is Ali Barkaye, who is now in Germany, and I will try my best to do my best this time, but from next week on, you will have the real thing with a brilliant physicist like Eli. Now, this is a course of electromagnetism, which whose aim is to some sense to integrate and to review many things that you have already been exposed to, which are the basic equations of electromagnetism, and differential equation, partial differential equation techniques for solving boundary conditions, and things that you have learned in the theory of wave, and things that you have to do with radiation, and things that have to do with what you have learned in opticals, and so on and so forth. The main goal of this course is to meld all these aspects together, because electromagnetism is such an important topic, and one of the important aspects of the course and of the theory of electromagnetism has to do with its intimate relationship with the spatial theory of relativity, that to some extent emerged from the attempt of physicists to deal with electromagnetic phenomena. So what Eli asked me to do in this, so it is quite important to understand how to write down the basic electromagnetic equations in a way that will emphasize their relationships with the theory of spatial relativity, which will be, this is something that will be done later in this course. Meanwhile, what Eli asked me to do is to give an introductory lecture that will cover the basics of the spatial theory of relativity that you have already been exposed to in the course of modern physics, in a way that I will try to emphasize those aspects of the spatial theory of relativity that are most relevant to the understanding of electromagnetism. Okay, so this is the goal of this lecture. I will not enter now into all the administrative questions of the course. I will leave it to Eli Barkaye to decide what is the percentage in your grades of the exam versus homeworks and so on. And instead, let us start directly with the principle of relativity. So, since you have started your education here in the department in the course of mechanics, I guess the first course that you have taken in physics, you were exposed to the idea of motions. Right? There are many types of motions. There are motion in a constant velocity, in a constant acceleration, and circular motion, and so on and so forth. And all the course of mechanics, Newtonian mechanics, was focused on the analysis of these types of motion. Right? Now, among these motions, there is a distinction between two types of motion. Motions that are inertial, meaning motion of a body at a constant speed on a direct line, right? And accelerated motions, which are all other motions. All motions in which the particle or object changes its speed or changes its direction of velocity are motions that are accelerated. And now there is a very important distinction between these two types of motion, which is as follows. suppose you are sitting in some closed car, spaceship, somewhere, I mean, between the stars, very far away from everything, and you have no windows. You can't look outside. And the question is, can you decide whether or not your motion involves acceleration or not? And the answer is that you can distinguish between these two types of motions, those who are inertial and those who involve acceleration. And how we are going to do that? By looking for fictitious forces, non-inertial forces, right? If it so happens that this spaceship is accelerated in this direction, suppose that this is the case, then if I am standing still here in the spaceship, I feel some sort of force that want to take me to this direction, right? And fictitious force, okay? And if I just, I'm opening my fingers and this goes down, it will go like that, okay? You understand? Actually, it will go like that because there is no gravity, right? So it will not go like that, it will go like that. So we can tell whether or not, without looking out, without looking through the windows, we can tell whether or not we are doing some accelerated, our motion is an accelerated motion or our motion is inertial by looking at the fictitious forces inside our frame of reference, our system, which is this car or spaceship or whatever you like. Okay? So for example, sometimes you may imagine that you are moving, maybe you are sitting in a car waiting in a traffic light and the car next to you starts accelerating forward and you have, sometimes your eyes not focused so much and you have the feeling that you're accelerating backward, right? For a second. Until you look out to the other side and see that the buildings and the trees are standing still. But you have the possibility to identify it even if you cannot look at the trees and the buildings by noticing that you are not accelerating forward as it would be the case if had your car accelerating backward, right? So this is and therefore, right, if we have two cars, say, moving with respect to each other, then we can decide which car is accelerating and which car is not accelerating by asking which car have a fictitious force. Okay, so this is what distinguishes between accelerated motion and inertial motion. Now, there is a very deep, important, and unanswered question in physics, which is there a concept of absolute motion, or does every motion only be a motion with respect to something else, right? So, for example, if we are saying that we have a spaceship, and when the spaceship accelerated in this direction, we have fictitious forces in this direction, or if it rotates around itself, we have centrifugal forces, right? The question is, with respect to what the spaceship is accelerating, right? And there are two schools in physics. One of the schools is saying that every motion it is meaningful to speak about motion only with respect to other material objects. So if I'm asking with respect to what object the spaceship is accelerating, the answer should be with respect to the galaxies, to the fixed stars, to some material object that is out there. Now, this implies that if we will do an experiment and remove all the galaxies, we will have no fictitious forces in the spaceship. This is called Mach's principle. And people are still arguing about it. So some people feel that there is no way this will be true. And, we have some notion of, absolute acceleration with respect to who knows, the ruler of God or whatever, something like that. And other thing that there is, motion is only a motion with respect to something else, some other material object. This is an ongoing debate in physics that we are not going to enter into, but still, when we are in our concrete world, with the galaxies being at the place they are, there is still the question of, there is still the distinction between accelerated motion, in which we have fictitious forces, and we can identify in a car without windows, and a uniform motion in a fixed velocity on a straight line, in which we have no inertial motion, in which there are no fictitious forces, and we cannot, in principle, we cannot tell apart if we have two spaceships now. One of them is moving with velocity v1, and another one is moving with the velocity v2. Then, of course, if they look from the windows at each other, they can see that they are in relative motion, but there is no physical experiment that will allow us to make it, to decide who is moving and who is standing still, or whether or not both of them are moving with respect to something else. This was a basic observation of Isaac Newton when he wrote down his Newtonian mechanics, right? And for that reason, Newton said that the state first, this principle of relativity, saying that in all inertial frames, which mean in all inertial frame of reference, which means all references that are moving in a fixed velocity on a straight line, one finds the same laws of physics. And the way to think about it more in a more mathematical manner. So suppose we are standing here. So this is our frame of reference that we call S, of course, and we look at this moving spaceship, which is the frame of reference S prime, and is moving with the velocity v with respect to us. So we assume that S is a fixed framework, and this is the spaceship, and here there is some particle, and there is force acting on this particle. Okay, and we know that F equals ma in the spaceship, right? So the guy who is living here can say that, so suppose F is given, like that's QE, right? Some given force, which is independent of the velocity, and this will be QE over M will be equal to d2 x prime dt squared, where what is x prime? X prime is the location of the particle with respect to this axis x prime, which is moving with the spaceship. Okay? Now, this is a description of an experiment from the point of view of an observer standing still in the spaceship. What will be the description of this experiment by the observer standing here? The answer is that we have to make, first of all, we have to make a connection between the coordinate x prime and the coordinate x. And this is very simple, because if this is a zero, right, of the x prime, it moves with the velocity v with respect to s. So we can say that x is x prime plus vt. This is exactly the relationship between x and x prime. And we also assume that the time is independent of the frame of reference. So what the pace of time in my watch is the same as the pace of time of in the watch of the guy sitting, standing or whatever, sitting in the spaceship, and therefore T is equal to T prime. These were the assumptions of Newton, and because of that, we can say that d2 dx squared of d2 dt squared, sorry, of x is d2 dt squared of x prime plus d2 dt squared of dt. But what is that? Zero, because v is fixed, is time independent. If we have acceleration here plus at squared, then we have a fixed contribution. But this is zero, and therefore the acceleration in the non-moving frame is the same as the acceleration in the inertially moving frame, and therefore the laws of physics are the same. This was the observation of Newton, and therefore Newton said that the laws of physics are the same at any two systems that are moving with respect to each other in a uniform speed on a straight line. Right? So you cannot, say it another way, you cannot tell apart one inertial system from the other. There is no preferred inertial system. And the way Huygens, I think it was Huygens, implemented that after Newton, he suggested another experiment in which you have, m1 moving in the velocity v1, and this is m2 moving in the velocity v2, and there is a elastic collision, and then you have m2 going with velocity u2 and m1 going with velocity u1 after the collision, right? And we know that if this collision is elastic, then m1 v1 plus m2 v2 equals m1 u1 plus m2 u2. What is that? Conservation of momentum. And m1 v1 squared plus m2 v2 squared is equal to m1 u1 squared plus m2 u2 squared. All this multiplied by 1/2, which is conservation of energy. And now this is a description of the experiment in the moving frame S prime. What's happened now the guy at this S, for this guy we have to add v to all these velocities. So all these velocities have to be, we should add v, which is a relative velocity between the two inertial frameworks to all these velocities. So let's write it now. Instead of v, I'm writing capital V just to distinguish between small v and 1, 2, and so on. So the first equation becomes m1 v1 plus v plus m2 v2 plus v equals to m1 u1 plus v plus m2 u2 plus v. Now, if this equation holds, the conservation of momentum, what is the condition for this equation to hold? So see, because of this equation, we can just cancel all these terms, right? So what we get is v times m1 plus m2 before the collision equals to v times m1 plus m2 after the collision, which means that if mass is conserved in the collision, then then there is the guy in the frame of reference S will agree that the law of conservation of momentum holds. Now, what's happened with conservation of energy?
Same.
Not exactly. So now it will be m1 v1 plus v squared plus m2 v2 plus capital V squared equals to m1 u1 plus v squared plus m2 u2 plus v squared. And now we have to open each of these parentheses. Now the first contribution will be, from here will be V1 squared and V2 squared, and this will be the same equation, right? The next contribution will be plus M1V times V1, right? So you can take the V out and you get this equation. And the third contribution will be the conservation of mass. So given the conservation of momentum, we know that the conservation of energy also holds. So both this person and this person will agree about the basic laws of physics, which is again the same idea that we have the relativity. We have we cannot tell which system moves with respect to the other by checking the laws of physics in both systems, because the laws of physics are the same, which will not be the case if one of them is performing an accelerated motion. Okay? Good. Now, so this was the basic feeling of physicists, let's say, at the year 1800. It's the opening of the 19th century. Then comes the 19th century, and at the end of the 19th century, all of the physicists would say exactly the opposite. Why? What happened during the 19th century that causes all the physicists virtually to switch their mind, by their opinion, by 180 degrees? The answer is the theory of electromagnetism. Why? The theory of electromagnetism was developed during the 19th century. Now I have a very important question, which is where is the eraser, if any? Very dead.
Maybe you can take back.
Okay, fortunately, okay. There is some price to pay for it, but I will use that. Okay? So during the 19th century, the theory of electromagnetism has developed from the Coulomb's law a few years before the French Revolution, so to Maxwell equation in the year 1860 something, right? And it did appear that the theory of electromagnetism implies that there is some difference between the laws of physics here and the laws of physics here. Why? For example, there is Ampere's law. What Ampere's law tells us? Can you remind me? Okay, a lot of time since you're under your first, yes?
The B field.
B field, yes. The magnetic. Every charge which is in motion, right? Every charge which is in motion, moving charge. When charge is moving, we call it current, and currents generate magnetic field. Right? So if this charge is moving, and I put here an apparatus that measures the magnetic field, a squid or whatever, some physical apparatus, I will find, I can be able to measure magnetic field. So clearly, if I'm putting this charge in my spaceship, right? If the charge is standing still in the spaceship, I will measure the magnetic field here, and I will decide if there is no magnetic field, it implies that the spaceship is still. If there is a magnetic field, I will decide that the spaceship is moving. So this will allow me to tell apart moving systems, two systems, to tell which system is moving with respect to who knows, so the ruler of God, right? With respect to the correct inertial system. There is only one correct inertial system, which is a system in which the charge standing still is not generating magnetic field. Another aspect of the theory of electromagnetism that yields the same idea is the discovery of electromagnetic waves by Maxwell. And we know that the motion of the speed of an electromagnetic wave is c, which is 1 over square root of mu naught times epsilon naught. Mu naught and epsilon naught are constants of the nature that has nothing to do with electromagnetism, right? That are related to static, magnetostatic and electrostatics. But we know that this will be the speed of light, right? And clearly, if now we are, yes, we are in a car moving, and the speed of light, right, is 3 times 8, 10 to the 8 meters per second. So if now we are in a car moving in this direction with the velocity c over 2, say, and we have a light ray going through here, and we will measure the velocity, the speed of this light ray, what we are going to get is only c over 2. Right? So we can tell apart standing still systems from systems moving in a constant speed by measuring, by a measure of the speed of light, and we can see whether or not the speed of light is a canonical quantity or something else. Once this was understood, many physicists start trying to check, can they show this effect? So it's very difficult to purchase a car moving at half of the speed of light. Of course, the effect is very small if the car is moving at velocities that we are familiar with in our life, right? Like 10 meters per second or 30 meters per second, which is, I guess, 90 kilometers per hour or something or so, right? It's very difficult to see the effect, but at the end of the day, Michelson and Morley were smart enough to devise an apparatus that will show the effect of the movement of Earth or something with respect to the true sitting system that they have attributed to the ether and whatever, and they performed the experiment, and the experiment failed miserably. They couldn't identify any evidence for this fact or related for the fact that the laws of physics, the laws of electromagnetism are different in this system and in that system, assuming that this one is really standing still. Then came Lorentz, and Lorentz understood. There is another point that I would not elaborate on, that you can use the same mathematical analysis, right, assuming that this is the transformation of coordinates between the system S and the system S prime. And I showed you that when you implement it to Newtonian mechanics, you find out that the same laws of physics are in S and in S prime, right? You can try to implement this to Maxwell equations, right? Maxwell equations are much more complicated, but you can try to do that and to see if you get the Maxwell equations in S, if Maxwell equations hold here, are they're going to hold here, and you find out that they will not, right? So Maxwell equations are not, how do you say it? No, the Maxwell equations are not the same, are not invariant to the transformation between S and S prime. And it was Lorentz who first suggested that you can change this transformation of coordinate, right? And Lorentz said, if you will change this transformation of coordinate to some other transformation of coordinate, then the Maxwell equation will be invariant. This was Lorentz's idea, but it was like a peculiarity. So what are you going to suggest me, that the time here and the time here are not the same time? It was kind of a mathematical peculiarity that Lorentz noted that there is some other transformation of coordinate that will leave the Maxwell equations invariant. Moreover, this transformation of coordinates that Lorentz had suggested will not leave the Newtonian mechanics invariant. There is a price you have to give up, or to give up the covariance of the Maxwell equation, sticking to the Newtonian or Galilean transformation of coordinate rule, or you will adopt another rule that will keep the Maxwell equation invariant, but the price will be violation of the invariance of the Newtonian physics. This was the situation at the year 1905, when Einstein first suggested to actually adopt the Lorentz transformation to the very end, meaning that we are going to give up the Galilean transformation of coordinates scheme, and to assume something else about the structure of space-time, and with that, of course, the Maxwell equations will be invariant, because this was why the Lorentz transformation was suggested to begin with. But we have to give up the Newtonian dynamics, and after 200 years of, perfect agreement with all kind of experimental results, after 200 years in which not only all physicists, all intelligent creatures in the world were convinced that Newtonian dynamics is the gold standard for absolute truth, it turns out that Newtonian dynamics is wrong. This was the idea of it. Okay. So what Einstein have suggested is another. So what Einstein suggested are two things. One of them, we have to move back to the relativity principle suggested by Newton, saying that there is no preferred inertial frame. All inertial frames are equally good. It's a complete democracy between inertial frames, of course, not including non-inertial frames, but all inertial frames are fine. And plus the velocity of light, the Maxwell equations holds in any inertial frame, which means that the velocity of light is the same in all inertial frames. Right? And this, as Einstein understood, will affect the structure of space-time through the new transformation of coordinates that we will introduce here. So what Einstein have suggested is a famous series of three Gedanken experiments, so thoughtful experiments. At the time of Einstein, at least nobody performed these experiments, but you may, once you accept these two principles, A, all inertial frames are equal, B, so the laws of physics hold in all inertial frames, B, the speed of light, or Maxwell equations, hold in all inertial frames, then you can get some clues as for the structure of the space-time. Now, what are these clues? First of all, we can go back now to our system S and S prime, and we can ask how one can suppose that there is a light bulb here, right? And at time t equals 0, and that the length of this spaceship is L. Now, at time t equals 0, t prime equals 0, right? The light bulb lights, and then there is a light ray going to this place and goes to this place. Now, the light bulb is exactly in the middle of the car. Okay? So, how much time it will take the light to go from here to here? L over 2C. And how much time it will take it to go to here? Exactly the same time. Meaning that I can synchronize the clock here and the clock here. If they both start working at the moment that the light reaches them, then they will be synchronized clock. They will show the same time. Right? This is a way to synchronize clocks. Now, and moreover, the event of light hitting this clock and the event of light hitting that clock happens at the same time, which means they are simultaneous. Technically, this is the word. These are simultaneous events they occur at the same time. Okay? Any questions? No. Good. So now, what happened from the point of view of Mr. X living on X? A. This is Mr. B in the spaceship, and Mr. A is standing here. And from this guy's point of view, when the light emerged from the light bulb here, right, or laser or whatever sophisticated apparatus, then it moves to here, still in the velocity c with respect now to this frame of reference, but this point is moving also with velocity v, right? So the time required to reach this point is larger than L over 2c. And on the other hand, the time required to reach this point is shorter than L over 2c, implying that the events of light hitting this apparatus, this watch, and light hitting this watch do not occur simultaneously, right? So simultaneity, we cannot speak about simultaneous events in the concept of simultaneous event is not covariant. It's not invariant. We cannot move with this concept from here to here. In every inertial frame, we can have clocks that are ticking at the same pace, so we can make them agree about the time, but we cannot do that between two frames of reference. Okay, so this was first experiment, first Gedanken experiment. Second Gedanken experiment was based on, say, light clock. What is a light clock? It's two mirrors, perfect mirrors, and the light is moving between these two perfect mirrors. The distance between these two perfect mirrors, right? The distance between these two perfect mirrors is h, and there is light moving from here to here at a speed c. Again, in this frame of reference, which implies that how much time it takes for light to go from here to here and back, it will be 2h over c. This will be the time unit of this clock. Okay? Now, what's happened here from the point of view of this guy? From the point of view of this guy, we have, right, this is our clock, and light is moving like that. Right? So if the time to go from here to here is, so this is, we call it T prime. This is a time unit in the moving system. What will be the time unit in this is the time unit in S prime system. What is the time unit in S system? Again, it's the time takes the light to go from here to here and back and forth. But now we know that the distance between this point and this point will be V times T. Right? Mm-hmm. If T is the time, yes. So now this is Vt over 2, and so this length, let's say L, right, is the square root of Vt, V squared T squared over 4 plus H squared, this is H, by Pythagoras. Okay? So the total distance traveled by the light ray when it goes back and forth will be 2L, so it will be 2 times, okay, we can write it as V squared T squared plus 4H squared, right? And the time, which implies the T, the time required to do that is 2L over C, right? So T is, so Ct, if you want, is the square root of V squared T squared plus 4H squared. Now this implies that T the time unit, so I have to raise both sides to the second power, right, and move things, and what we will get is that t, we have c squared minus v squared, so we have 4h squared divided by c squared minus v squared, square root of that, right? Just algebra. Hopefully I did it right, which implies that t is 2h over c times 1 minus v squared over c squared to the power of 1/2. Right? Now this is a very important quantity. If we will define beta as v over c and gamma as 1 over square root of 1 minus beta squared, so gamma is also 1 over square root of 1 minus v squared over c squared, we can write that as, so we can find that t is equal to 2h over c. What is 2h over c? T prime. Times, so it's gamma times t prime. Now, what is gamma is bigger than 1 or smaller than 1? Bigger than 1. Gamma is bigger than 1 because we divided 1 by something which is definitely smaller than 1. So gamma is bigger than 1, and because gamma is bigger than 1, t is larger than t prime, which means that the time, 1 unit of time of the static clock is takes longer in the frame of reference, which is moving with respect to the static clock, right? Very important that if this is the clock we'll see here, it will be the other way around, right? This is the increase in the time length, so it implies that if this is not a moving now a moving spaceship, but suppose an elementary particle that disintegrate after 10 to the minus 10 seconds, right? So this elementary particle have some kind of clock inside its guts, and when this clock ticks 10 to the minus 10 seconds, it will disintegrate. If this elementary particle is moving in a very in high speed with respect to ours, we will see that it disintegrates over larger and larger and larger time scales. And for that reason, like muons that have I guess disintegration time of about 10 to the minus 6 seconds, so they can travel, even if they travel in the speed of light, they travel like a few hundreds of meters before disintegrating. Still, we can get here on the surface of Earth muons that were generated in the high atmosphere 10 kilometers above us, because they are moving in such a high speed that in our framework it's much longer. Time. So essentially, the moving guy will be younger with respect to the guy who is sitting here, and vice versa, right? And vice versa. Good. So so this is the second thought experiment of Einstein. Another thought experiment is the third one, is just almost to the second, but now we rotate the light clock by 180 degrees. Again, it's h here, and the light is going back and forth. And again, the time in the prime frame will be exactly this time unit. Okay, because who cares? The clock is standing still in the moving frame. But what's happened from the point of view of Mr. A in the static in this frame, in frame S, now the time required to go from here to here, right, from this point to that point, will be what? Will be h divided by c minus v, because the relative velocity is c minus v, right? Light moving in velocity c, and this side is moving in velocity v. This will be the time, let's call it t1, the time to go from here to here. And the time for the back side of the journey, t2, will be h divided by c plus v. Okay? So the total time required to go back and forth will be t, the total t, which is t1 plus t2, from the perspective of the guy in the S system, is h divided by c plus v times c minus v. I'm taking a common denominator, okay, this plus that. And then here I should put c minus v plus c plus v, so I'll get 2c, right? So I will get 2c here, and this is 2ch divided by c squared minus v squared, which is 2h divided by c, now, times 1 minus v squared over c squared, which is gamma squared times 2h over c. Okay? Now we see a contradiction, because before we decide that t is equal to gamma t prime. Now 2h over c is t prime, okay? And now when we rotate our clock by 180, by 90 degrees, right? So the direction of light is parallel to the direction of motion. Then we got, instead of gamma, we got gamma squared. Okay? And the only way out is to decide, so what we have gotten is t prime is gamma squared times t, which cannot be true because we have decided that. And the only way out is to understand that h is shrinking. So h in this coordinate system is not h, but h over gamma, and this will compensate, right? And this is the contraction of length. So every length that is parallel to the direction of motion is contracted by a factor of 1 over gamma. Every length that is perpendicular to the direction of motion undergoes no contraction, and you can show that by an experiment, right? You have a scratch. You have something like that with that can leave a scratch in this system and vice versa, and you can see that if the height of the scratches is not the same, then they are moving at different velocity. You can say who is moving and who is not. So it must be like that. Okay. Yes.
I don't really understand. Why do you compare the second thought experiment to the third one?
Because in the second thought experiment, we decided that the pace by which time elapses in system S is larger by the pace time elapses in S prime by a factor of gamma. And here we did the same thing, and we got a factor of gamma squared. So they contradict each other unless you understand that h is also divided by 1 over gamma, so you have the same gamma factor.
Why must it be the same? Why must?
Because the pace of time is the pace of time. If the pace of time is different, if you put a clock like that, or if you put it like that, then you can say which system is moving and which is not, right? So the pace of time is the pace of time, right? Which also implies that everything, also biological processes, every process should have the same effect of time dilatation or length contraction, because if anything else is not satisfying this relationship, then you can identify who is moving and who is not. Okay. So this brings us to the Lorentz transformation, right? So now we can put forward let's first just to clarify things. Let's first describe in more detail this idiotic transformation that people are calling Galilean transformation. Of course, Galileo was, if you will say Galileo that this will be called after his name, then he was insulted because he thought it's kind of trivial. But once we discovered some alternatives, then it was giving it a name. So this is a Galilean transformation. And the Galilean transformation is xt, or let's say, xt is equals to x prime t prime, and now we have 1 v 0 1. That's a Galilean transformation that tell me if an event happens at x prime and t prime in the prime system, what will be x and t in the S. Okay. Now, what's happened if an event happens at xt here? How do I translate it to the to the guy here in the S prime system? Right. Clearly, all I have to do is to put a minus in the v, right? Because that's the only difference. So I can say that x prime t prime is equal to 1 minus v 0 1 x. Right? Note that if I multiply this matrix by that matrix, what I will get? Unity. Why? Because if I'm going back and forth, then I'm back into the same inertial form. Okay? Now, what is Lorentz transformation? Lorentz transformation tells me that x prime t prime x t. So I have, first of all, I have a gamma here, right? And 1 v over c squared v1, wait, is that true? No, the other way around, sorry. So v over c squared 1, and this gamma. Very important. And the reverse Lorentz transformation is, of course, again, I just have to invert the sign of v, so it will be gamma 1 1 minus v over c squared. And you can check that if you multiply this matrix by this matrix and also multiply them by gamma squared, you will get the unit matrix. So if you go back and forth, you go back to the same place. Okay, now let us try to understand what track the implication of the Lorentz transformation. Of course, this is something that should be exercised because it leads to a lot of confusion. But you know, this is what you are supposed to learn in the course of modern physics, so I can only mention it. So suppose in the system S prime, I have one event at time 0 0, right? Between x equals 0, t equals 0, and one event at 0 t prime. Now, this event is, say, this guy start moving, and this event is this guy is still standing still here, so its x is still 0 in this coordinate system, but it waited time t prime. So it waited 1 year in his watch. 1 year have elapsed from the beginning of the motion to this point. And the question is, what will be the corresponding events? What will be the coordinates of the corresponding events in the system S? Right? You understand what I'm saying? Okay. So what will be the corresponding event for which transformation we are going to use? This one. Right? No, sorry, it's the other way around. It's this one. What's going on? I did the mistake. Wait. Okay. This is fine. Okay, fine. So we are going to use this transformation. Good. Okay. Now, That's too bad that nobody have noticed it, because it implies something about your... Okay. So if x prime and t prime are 0 and 0, what will be x and t? 0 and 0. Right? So the both systems agree about the can agree about t equals 0 and x equals 0, the origin of the coordinate and the 0 of time, and if not, then they can gauge their clock such that they will agree. No problem, because you can emit, you know, this system may be close as much as you can to each other, and you can emit a light ray that will go from here to here at 0 time and synchronize the clocks. Now what's happened here? What will be the coordinate of this event in the system S? So I'm using my Lorentz transformation, and what I will get? What will be x? X will be 1. So x prime, again, this vector is now 0 and t prime, right? So I should multiply that by this, and I will get gamma times v times t prime. This will be x in system S. And what will be the time t will be what? Will be gamma times t prime. Now, what we have seen here, we see first that, okay, sorry, I call this t capital T, right? This is capital T prime, and this is capital T. So you see that capital T is gamma times t prime. This is exactly the effect of time dilatation that we have already discovered, right? And now what is that? X is gamma times v times t prime. But what is v times, what is gamma t prime? We know that gamma t prime is t, right? So what is written here is simply vt, which is good, because if this spaceship is moving with respect to us with a velocity v, then at time t of our watch, we are going to see it moving v times t, right? So everything is good, and you can derive all the Gedanken experiment that I described before by looking at by implementing the Lorentz transformation. And what is important is to understand the idea of event and so on and so forth. Another implication of the Lorentz transformation. Let us assume for the moment that we have now 3 frames of reference: S prime, which is moving with velocity v1 with respect to s, and S2, S double prime, which is moving with the velocity v2 with respect to s prime, right? Not with respect to s, with respect to s prime. And we want to know what will be the velocity. So okay, let's. This is v21. This is v10. Right? And this is, and I want to calculate what is v20. So what is the velocity of this frame of reference with respect to this one? Okay? How I will do that? First of all, I will take this point, and this point is 0, 0 in the system S double prime. Right? And now I know that the coordinates of this point at S prime will be v21 times t prime, right? That's x, and what? And t prime, right? If a time t prime elapsed and at this frame of reference, and I have colored a point here, then after time t prime in this frame of reference, it moves v21 t prime, and the time is t prime in this frame of reference. And now I should take this, put it here, and calculate what will be x and t at the system V. So I will find that x and t will be what? Now I have, will be gamma times 1 v10, the velocity, relative velocity of these two, minus v10 over c squared and 1 times v2 t prime and t prime. Okay? So note that the gamma and the t prime are going out. So we have gamma times t prime times v2. This is v21, sorry. v21, yes. So v21 plus v10, right? And here I will have
you forgot the minus.
You forgot a minus.
V.
Which minus? This minus is not here. Sorry. Sorry?
No.
No, like on the right side, both of them.
No, it's
Yeah, it's good.
Yeah,
This is it.
Yeah.
This is it. So I have 1 plus 1 times v21 plus v10 times t prime, and I took the gamma and the t prime out, and now I have 1 plus v10 v21 divided by c squared. So this will be x at the system S, and this will be t at the system S. Now what is the velocity? The velocity is x over t. So the velocity v20 is v12 plus v21 plus v10 divided by 1 plus v10 times v21 divided by c squared. This is law of addition of velocity, Einstein's law of addition of velocities. Instead of just adding the velocities, like in the Galilean dynamics, v120 is v21 plus v10, right? This will be the addition of velocities under Galilean dynamics. Now we have this extra factor, which implies, by the way, that if, for example, v10 is c, what we have here is c plus v21 divided by 1 plus c times v21 divided by c squared, which is c. Okay, so if something is moving at the velocity of light in one system, it will still move in the velocity of light in another system, despite the fact that the systems are moving with respect to each other, and the reason is this extra factor that was added to the Galilean law of addition of velocity. Again, I must remind again that the name, Galilean here is sort of imposed ex post facto, and because everybody thought these are trivial, the Galilean, there is no other alternative to the Galilean transformation until it was discovered that indeed there is. So this is like, people that were insulted by naming something after their name, like Kronecker. Yes, Kronecker was a great mathematician, but at the end he is associated with the fact that if I and j are equal, then it's 1, and if I and j are not equal, it's 0, the Kronecker delta, which is kind of trivial thing. Also, Levi-Civita, others, Heaviside, beta function, all kind of. Okay, good. What I did until now was to speak about the Lorentz transformation in 2 dimensions, x and t. Right? Now, first of all, I would like to present the general Lorentz transformation. So the Lorentz transformation in 4-dimensional space, which is now t, x, y, and z. And to do that, I am note that I am taking t and putting it first. Right? So the general Lorentz transformation, t, x, y, and z, is equals to a 4x4 matrix times t, x, y, and z in the prime system. And now what makes the x coordinate special is that I take the x coordinate to be the direction of the relative motion. Right? If not, if it goes in the y direction, then you have to change it, but it's a trivial change. And of course, what I have here is gamma, yes. So here I have gamma v, and here I have gamma v over c squared, and here I have 0, 0, 0, 0, and 0, 0, 1, 0, and 0, 0, 0, 1. Right? The y and the z.
The opposite in gamma v and gamma v.
Yeah, of course. Yes. Because I exchange the location of the t and the I. So this is the most general Lorentz transformation, and you can immediately understand what will be the backward transformation. And again, the only thing that to emphasize is that x is not just a randomly picked direction; is a direction of relative motion between the two systems. Okay. Now, many things to say about that. Okay. What about people who are working in special relativity do not like this transformation because it looks ugly. Moreover, they started thinking about such transformation like rotation, right? You know that if you rotate things, for example, you have x, y, z, may be written as, I don't know, x prime, y prime, z prime, and now we have cosine theta, sine theta, minus sine theta, cosine theta, 1, 0, 1, right? This is a rotation in the xy plane, right? You're familiar with it, of course. So what this rotation implies? It implies that there is no actual distinction between x and y, right? Maybe I am looking at the tables here, and I can make a distinction between their width and their depth, right? As long as I'm looking at it from here, it's very nice. But once I'm going from here and I'm looking from another angle, right? Then okay, the idea of width and depth are no longer independent physical ideas, and I have to think about a way to rotate my coordinate system. So this is like what is x prime, y prime, and z prime is when I'm looking from here, and x, y, z is when I'm looking from here, and now width and depth are not the same quantities anymore. And I have to change my frame of my way, the way I'm looking at the system, right? So in the same sense, people started thinking that what this transformation expresses is the fact that x and t, like the x and y, were mixed when I look at it like that, right? X and t are mixed through this transformation, right? So it's like a geometrical transformation, not a rotation. But it's a kind of generalized rotation, if you like, that mixes not x and y or x and z, but x and t or y and t and so on. Mixes between time and space. However, there is a technical problem here, because when I'm measuring lengths, like in the depth and the width, usually I'm using meters for both, right? If I was using meters here and feet here or some other unit of measurement, then when I'm trying to change my coordinate system, it will be a mess. Okay. On the other hand, here we will measure x in meters, but t in seconds. Right? So this is a problem, just technical problem of using different units for the transformation. So what people are what many people are doing is they are working in the coordinates ct, x, y, and z. And now this is also meter, because this is time times the speed of light. So 1 second of length is 3 times 10 to the 8 meters, or 1 meter of time is 1 over 3 times 10 to the 8 seconds, if you like. And if you use that, then the Lorentz transformation So this is ct prime, x prime, y prime, z prime. And I will not do the algebra, but you can check that here you get gamma, gamma beta, gamma beta, gamma, 0, 0, 0, 0, 1, 1, something like that. So the Lorentz transformation becomes very nice. I mean, you can very easily remember that. And moreover, you the time and space are now expressed in the same units. This is now okay. This is one thing, and this also allows us to understand, to demonstrate better the structure of space and time in spatial relativity. Because now we can speak about X and CT, right? These are two objects that have the same units of meter, okay? And if this is 0, 0, what is this line at 45 degrees? Right?
X equals CT.
X equals CT, which means something that moves in the speed of light. Right? Something that moves in the speed of light is going along these purple lines, right? And everything should move either in the speed of light, which is light, or slower. So this is a legal motion, and this may be a legal motion provided that the slope is never larger than 45 degrees, right? But this is an illegal motion. This cannot happen. And therefore, using this coordinate, physicists are speaking about the classification of all the space-time, right? To all these points are points that are called future. Why they are called future? Because this point can affect all these points by sending some signal that travels equal or lower than the speed of light. So this is future in the sense that every event here may be caused by an event here. This is past. Why? Because this event may be caused by an event here, and both this and that part are calling time-like. So time-like intervals. So the interval between this and here is time-like, and the interval, this interval is time-like. On the other end, this interval is space-like, right? And if the interval between two events are space-like, then we can say that none of them may be the cause of another one. Okay? So this is the region where causality cannot happen. This is the region where there is no causality. There is no causality between two events that are space-like with respect to each other, and there is a possible causality between two events that are time-like with respect to each other. Is that okay? Fine. Now, by the way, you may even the question of whether or not this event happens before this event is meaningful. There is no Lorentz transformation that will make this event happens before this one. Because if there was such a thing, then we have no causality. Okay? On the other hand, the question of whether or not this happens before that is meaningless because it's a frame of reference dependent. You have a Lorentz if this happens before that in this frame of reference, there will be another frame of reference where this happens after. Okay? Look. So if you meet a fortune teller or somebody who is telling you what the future is, which is a very tricky thing to do, you can ask him or her to have a modest feature and to tell you what happened here, right, in the future, but out of our lifetime. That this is as impossible physically as telling the future. Okay. Now, there is the most importantly, you know, why physicists like vectors, right? Why we are writing f equals ma and not fx equals max, fy equals may, and fz equals maz. Wait, before that,
It's longer.
we like this expression instead of that one because this expression tells us something important. It tells us that if now instead of looking at the system like that, we will look at it like that, right? Looking at things differently, right? Then the xyz will not be the same xyz, but the transformation of all vectors is the same transformation. fx, fy, fz will satisfy z with respect to fx prime, fy prime, and fz prime. So when we are writing it like that for the a acceleration and the force, we are saying, okay, both acceleration and the force are subject to the same transformation. And therefore, if this relationship holds in one system, in this system, it will hold also in that system. You see? Okay? So this is a vector, and the meaning of expressing relationship in terms of vector, the meaning is that this relationship is invariant to the change of coordinate system. We will get the same relationship in the rotated system. And the same is true here. So if we call such a thing a four vector, okay, then if we can, and the way people are usually, the notation used here is not an arrow above the thing, but, right? So x mu, right, is a four vector, say, of ct, x, y, and z. Not necessarily, it can be also t, x, y, and z, but a four vector is something that undergo transition from one frame of reference to the other frame of reference under this Lorentz transformation, right? Like a vector is something that going from here to here under such a rotation matrix. The four vector is undergoing transformation from prime to non-prime under Lorentz transformation. Do you understand that? Right? And then if I'm writing something like, I don't know, A mu is equal to alpha B mu, right? If I'm writing a law of nature in a way that relates one four vector to another four vector, it implies that this law of nature will be covariant, it will be the same in any coordinate system, that in any frame of reference that are connected to each other by the Lorentz transformation. Now I'm going to your observation. In rotations, we know that there is a quantity which is invariant under rotation. What is the quantity which is invariant under rotation? The length of the vector, right? If I have a vector x, y, z, then L, say, which is x squared plus y squared plus z squared, x squared, this quantity, or the square root of that, is invariant under rotation. So the x and the y and the z will be different when I'm going to the tribe of people who are looking at everything like that, but the length of the vector will be the same. Okay? There is in parallel with that, right? There is something that is kept invariant under the Lorentz transformation, which is the interval. The interval is minus t squared, or c squared, t squared, plus x squared, plus y squared, plus c squared. That's all. Right? Okay? Now, first of all, you must know that there are two schools in there is this is called so this interval is like multiplying two vectors. This is like multiplying x, y, z by a matrix, and here I have x, y, z, and here I have 1, 1, 1. Right? Okay? This interval is like having ct x, y, z multiplied by ct x, y, z through the matrix minus 1, 1, 1, 1. Right? This is a metric of the space. Now there are, unfortunately, two schools in physics. This, I guess, is called the West Coast matrix, and in the East Coast, people are using this matrix. 1 minus minus minus. Doesn't matter. So this will be plus, and all this will be minuses.
What's the difference?
No difference except of confusing the student. I mean, historically, it so happens that in the West Coast they were using one matrix, and in the East Coast they were using another matrix, and when people have realized the disaster, there was already so many papers doing that way, and there are so many papers doing this way that you cannot stop the craziness. So it's a completely idiotic and irrelevant thing, but I asked Eli, which matrix you want me to use, and he said use the metric of this book of Griffith. So this is Griffith, but you should know that it makes absolutely no difference except of having this plus minus 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 in the other. So if you see something like that, it's just I mean, it's a disaster, but there is nothing to do about it. Okay? It's like, you know, driving in the left side or driving in the right side, right? Nobody wants it to be different between different countries, but since it's so difficult for people who are driving one side to move to the other, it so happens that there are states like that and
How
states.
does it even equal?
Hmm?
Like, why does it even equal between the
Why this quantity is invariant under
Yeah,
the Lorentz
like-
transformation? Just check, plug it in and see that this quantity is invariant, right? And in this language, the distance between two events here is, since it's time-like, it implies that this quantity is larger than that quantity, right? So this is plus, sorry. Here the interval is minus, and here in the interval is negative. Here and here the intervals are positive. And by the way, this is two-dimensional. Of course, if you are going to higher dimensions, then you have like y here, and this becomes a cone. This is a light cone, the purple thing. And if you and if it's in 4D, then we can. I mean, if you add the z, we cannot plot it anymore, but it's still called the light cone. During the first part of this lecture, we have explored relativistic kinematics and the structure of the space-time. Now, the rest of this lecture will be devoted to relativistic dynamics, i.e., to the ideas in relativistic mechanics that are the analogous of Newton's law of motion, like F equals ma, and to the conservation laws. We'll start with the conservation laws, then we will move to the force law. So, first of all, we would like to define a velocity. So, if we are in a system S and we have a particle, or in system S prime, and we have a particle moving at speed v, then v, let's call it v prime, then we know that v prime is dx prime dt prime. Such a quantity is not part of a 4-vector. Why? For two reasons. First of all, this quantity is 3-dimensional. Okay? So we can solve it by writing a 4-vector of the type dt prime, dx prime, dt prime, and so on. This will be a 4-vector, right? But what is dt prime, dt prime? 1, right? Okay. this this will have the form of four. This will have four components at least, which is a prerequisite for being a 4 vector. You want to have 4 components, but a 4 vector is not only a vector with 4 components, but a vector of 4 components that transform from one system to another system through the Lorentz transformation. This is a 4 vector, not a list of 4 objects, but 4 objects that satisfy the Lorentz transformation. And this thing will not satisfy the Lorentz transformation. Why? Because X will satisfy the Lorentz transformation, X, T, and so on. But now we are dividing by T, so it cannot satisfy the Lorentz transformation. If we will have, it is usually done that people are defining eta as a 4 vector of eta mu, right? Mu is like that, as dx mu, x mu is x0 is, this is x0, right? x0, x1, x2, x3, if you like, right? So x0 will be ct, that's fine, but we have to take the derivative with respect to something which is invariant. In order for z to be a 4 vector, we cannot take the derivative with respect to t, we have to take the derivative with respect to something which is invariant. The invariant quantity that we put here is called tau, and it is known as proper time. Proper time is a bad translation to English. They meant eigentime, but there is no, the word eigen, עצמי, does not exist in English. So
but there is a word like self-time.
Proper time, that's a standard nomenclature, but they meant eigentime. And it means זמן עצמי, meaning that this is a time, so the relationships are gamma tau equals t. Meaning what? Meaning that if the time t, if t is the time measured in the s coordinate system, then tau is the time at the watch of the particle, right? That's when the particle starts being hungry after eating breakfast, right? How much, when it will start feeling hungry again, the answer is determined by tau. So tau is the time, but which time? Not the time of this system, but the time of the moving particle, right? And this quantity, indeed, which is of course equals to, so d d tau is d dt dt d tau, so it's gamma dx mu dt, right? This is a 4 vector. Now, this is again what it is. It is gamma times dct dt. What dct dt is? C. And now we have gamma vx, gamma vy, gamma vz. This is a legal 4 vector that undergoes transformation under this under the Lorentz matrix. Okay, now there is a lot to be said about this and the law of addition of velocities and so on and so forth. I am not going to go into that because I have no time. Instead, I will jump immediately to more important quantities with respect to mechanics. And the most important one is P mu, the 4 momentum. This is a 4 velocity. You see that this is like not something that is have a lot of physical meaning. Oh, it does. But the 4 momentum is more important. So the 4 momentum is Px, Py, Pz. And okay, so first of all, maybe I will not erase it, but I put it. So the 4 momentum is simply m, that I will elaborate on in a moment, times eta mu. Right? It's like momentum is mv. 4 momentum is m times eta mu. And so what I will have here is m gamma vx M gamma Vy, M gamma Vz. I want you to remember that gamma depends on V. Gamma is not, sorry, I have erased. Gamma is 1 over 1 minus V squared over C squared square root. So gamma depends on V. It's not something that, right? And here we will have M gamma times C. Now, what is the four momentum? This is X. These are X, Y, and Z components of the relativistic momentum. Note that it converges, right? If we are going at slow velocities, what we are going to get? At slow velocities, gamma equals 1, and we will get mvx, mvy, and mvz. So it converges to the standard momentum at the limit of velocities that are much smaller than the velocities of light. And this quantity is simply the energy divided by C. That's where, of course, one can motivate it, but let's take it as a definition. This is what you have to know in order to make calculations. So what we see now is that E, what's important, E is, according to that, defined as M times C baribua, C squared, divided by, which is times gamma, which is minus V squared over C squared. Okay? This is that. So this will be the definition of the energy. And what is that energy? If I now assume that V is much smaller than C, so I can expand it, and I will get mc squared, right? Times 1 plus 1/2 V squared over C squared plus something that goes like V, I guess, over C to the 4th or something, some coefficients, 3/8 or so, right? So what we get is, to the leading order, we get mc squared plus 1/2, and the C squared cancel, mv squared plus something that goes like 1 over C squared or C cubed or something. Right? Now, what is that? This we know what is that. This is the kinetic energy in the Newtonian mechanics. Right? So this is the kinetic energy. Now, what is that? This implies that every particle of rest mass m, so now we understand what is the m I have written here. M is the rest mass of the particle. Is the mass of the particle when we put it on a weight, when we try to judge its mass. This is the mass of the particle when the particle is at rest, when its velocity is 0. Right? We have energy associated with the mass of the particle with the famous relationship E equals mc squared. And the first correction, okay, because if we have a moving electron, we can neglect that as long as the electron do not disintegrate or do something, right? Or annihilate it with another positron, or who knows. As long as the electron stays an electron, we can take this as a constant. So it just changes our energy, but we know that energy is always measured with respect to some arbitrary 0. So this will define the 0 of the energy. And then we have this term that is the leading order, which is the kinetic energy, and other terms that we can neglect in the limit of Newtonian physics. Okay? When these terms start to play a role, when things are changing their mass, for example, when an uranium atom, nucleus, disintegrate into xenon and iodine, or who knows what garbage, and sorry?
No.
The total mass of the product nuclei is smaller than the total mass of the uranium nucleus. And the extra, and the difference between them is converted into energy. And this is what you are doing when you have a nuclear explosion. you convert mass into energy, and you know that like Hiroshima bomb, I guess, if I remember it correctly, correspond to 1 gram of mass, total 1 gram of mass converted to energy, right? So because of this is squared, right? The exchange relationship is very expensive. Good. So this is the rest mass. This is the momentum vector. For vector, it undergoes a transformation from one system to the other by exactly the same matrix. There's nothing else. And and most importantly, we have also something which is analogous to the interval, a conserved quantity that will be the same in S prime system and in S system. What is this conserved quantity? Again, it's by structure. It's a time quote-unquote component with a minus squared plus adding the space component with a plus. So now the conserved quantity will be minus E squared over C squared plus Px squared plus Py squared plus Pz squared. And this will be conserved. Now, what will be this will be equal to what? Exactly, because we know that if the particle is standing still, then its energy will be mc squared, right? And therefore, if the particle, and we know that for a particle in a movement, right, this quantity will be the same as for a particle which is standing still, right? So if the particle is standing still, E is mc squared, E squared is m squared c to the power of 4, right? So this will be equal to minus m squared c squared. This is a dispersion relation that is usually written as E squared minus P squared C squared. P is the total momentum, so it's Px, Py, Pz, right? Is equal to m squared C to the 4. Right? Dispersion relation, which, by the way, also implies that if you want to calculate P, so P is the square root of E squared over C squared minus m squared C to the 4. Why do I C squared? Right, something like that. I'm not sure that I want it. Okay, forget about it. One important aspect of the theory of relativity, which is very relevant to the course of electromagnetism, is the following observation. In Newtonian physics, in your mechanics course, you did not allow particle of mass 0. Why?
Because you don't interact with any other mass.
Why? Okay, exactly. Since F equals ma, if you have a particle for which m is going to 0, every force will cause it infinite acceleration and will disappear to infinity. Right? So you did not take into account particles with 0 mass. Special relativity allows us to have particles with 0 mass, right? Provided what? That if this is 0, then E is equal Pc, right? And this implies, this is a dispersion relation for the photon, right? For light particles, or every particle which has 0 mass will satisfy this relationship, which implies, by the way, that it is moving in the speed of light. So 0 mass particles are allowed provided that they are moving in the speed of light. Good. Now, having learned all that, okay, okay, I want to emphasize another distinction, which is a distinction between a conserved quantity and invariant quantity, right? Conserved quantity, like the momentum is conserved. What does it mean? That if we have a collision, then it will be the same before and after the collision. Not to be mixed with invariant quantity, which is a quantity that will not change its numerical value when I move from one system to the other. When I move from S prime to S, every of these terms will change. They will be still conserved in collisions, but the numerical value of this and that will change. Still, the numerical value, this relationship still holds, right? Or the rest mass is conserved, right? Okay. So to begin with, let us think about two particles, one of mass m, which is moving at the velocity 3/5 of the speed of light, and it collides with another particle with a mass m, which moving at the velocity 3/5 of the speed of light, and they will hit each other in a perfectly inelastic collision. So they will merge. What you call plastic collision. Perfectly inelastic collision, they will merge with each other. Right? How do we analyze that in Newtonian mechanics? We are saying, okay, the total momentum is before the collision is what? 0. So the total momentum after the collision will be 0. So this merged particle will move to what direction? Standing still, right? And what will be its mass? The total mass, right? The total mass will be 2m. This will be its mass. And where the energy have gone? What? What is the energy? It has a kinetic energy. What? Heat. Of course. This red thing will be hotter. Okay. Now, what's happened in relativistic mechanics? Of course, there is no point in Py and Pz here. We can relate only, or we can take into account only E and P. So I know that before this, let's call it this 1 and this 2, right? And this will be 3. Now, 1 have energy was m. What is gamma? Gamma of 3/5 is what? You put it there, right? This is 1 minus 9 divided by 25. So 16 divided by 25, square root is 4/5. So it will be 5/4, right? So gamma is 5/4. Of course, this is why I've chosen the 3/5, right? And this will be m times gamma times c, and m times gamma times Vx, which is whatever, right? Times Vx. This is particle number 1. What about particle number 2? Before the collision, the momentum is exactly the opposite. And here I have the same m gamma c. Now what's happened after the collision? Particle number 3. So we know that why we are interested in momentum, because it is a conserved quantity, because it equals before and after the collision. So this plus that is what? 0. Exactly like in Newtonian mechanics, it will give us 0. And what is this plus that? Now the total will be 2m times c. However, we have an extra factor of gamma. Now gamma is 5/4, and therefore the total energy of particle number 3, this one, will be what? Will be 5/2 mc squared, right? Because this is E over C.
Yeah.
It's not energy. It's E over C. So the total energy will be 5/2 mc squared, which includes the 2 mc squared due to the mass, but also half mc squared due to the energy. So the heat is also included, meaning that hot things are heavier, right? And it's true. If you heat something, it is becoming heavier, and the gravitation acts on it strongly. Right? If you balance two objects on a weight and you hit one of them, it will go down. Of course, you can't measure it, but in principle, it is going down. Okay? So there is no distinction between energy and mass in the special theory of relativity. These are the two sides of the same coin. Okay, let's make another example. Which is we have an elementary particle named pion that disintegrate into a muon and a neutrino. Don't be frightened by the names, it's only names. Or there are elementary particles like that are disintegrating, and this is the legal disintegration process. And the question is, you want to know what will be the energy of the muon after the disintegration. Of course, they must move on the same line. Why? This is still conservation of momentum, right? Momentum before disintegration, 0. After disintegration will be also 0, so they must move on the same line that we can choose arbitrarily to be our x direction, no problems. And we, okay, so how do we analyze that? We can say that before the disintegration, we have here E pi over C, and the momentum of the pi meson was 0 because it was standing still before the disintegration. After the disintegration, we have E muon over C and P muon. This is 1, the energy and the momentum of the muon, plus E neutrino over C and P neutrino, and the P neutrino is in the other direction. Okay? Now, the important thing here is to assume, this is not true, but it's still a question that they are putting on the textbook, because once upon a time, the mass of the neutrino is not exactly 0, but very close to 0. So neutrino for this question is a massless particle, right? And if neutrino is massless, we know that E equal PC, which means that P is equal to E over C. So the energy and the momentum are the same. The two, these two entries of the 4 vector are the same because of this relationship for a massless particle. So this is our assumption, and this implies, of course, that P of the muon is minus E of the neutrino over C. This is one equation. The other equation is the E of the pion is equal to E of the muon plus E of the neutrino, right? Because I will multiply with everything by C, right? So what I still don't know, I want to find E of the muon. That's my goal, right? E of the pion, I know what it is. It's just the mass, the rest mass of the pion times C squared, because it was at standing still before the disintegration, right? So I have to calculate the E of the neutrino in order to express it by these two things. So now I can implement what? Now I want to implement the dispersion relation, and I want to say that C times P of the muon, is equals to the square root of E muon squared minus M muon times C squared times C to the 4. Yes. Okay? So I implement the dispersion relation for the muon, which is that. Okay? And this implies that what? Okay, so I can put it where? Okay, now this is E of the muon is minus, I want E of the neutrino, right? So now I know that E of the, and this is simply E of the neutrino with a minus sign for me, from the conservation of momentum. Yes. So I can write that E of the muon is M of the pion times C squared minus E of the neutrino. But E of the neutrino is minus that, so it's plus square root of E of the muon squared minus M of the muon C to the 4th. And now I have only algebra, right? The only thing that I have is to algebraically calculate. I mean, I have E muon and M muon and M muon and M pi are given. So I have to find out what is that, and it's only algebra. So I'm not going to go into that, but just to give it as an example. Another example on which I will elaborate even less, because I'm not interested in, teaching you particle physics, just to exercise or some exercise of how to use the conservation laws and the dispersion relations. So suppose we have, like this famous thing, the Compton effect. Compton got the Nobel Prize for this calculation. We have a photon with energy E0, and this photon hits an electron. The photon is going to here with energy E1, and this is the electron which is moving to here with some velocity, and we will take this as the x-axis, and this will be theta, and this will be phi. Okay? Now the challenge of Compton was to calculate E1 as a function of theta. Okay? And how to do that? Again, before we have the total momentum, 4 momentum, but now it's not a one-dimensional problem, it's a two-dimensional problem. So we will have to define this. It will be x, this will be y, and z will not be part of the story. And we are going to get, before we have, for the electron, we have m electron c 0, 0, meaning that this was the E over c for the electron, standing still. This is the momentum of the electron before the collision, which is 0. Plus, we have E naught over c and E naught over c and 0. 0 because it is moving in the x direction, and E naught over c is the momentum because we know it's a massless particle, so E naught over c is both the energy and the momentum. This is equal to what? What's happened after? After I have E1 over c here, and here I have E1 over c times cosine theta, and E1 over c times sine theta, plus now I have m gamma, m electron gamma times c, and I have p electron cosine phi and p electron sine phi. Right? These are the equations. What I do not know, I do not know phi. I have to solve for phi and for the p electron, right? So I'm using this equation to solve for phi, and then I'm using this equation to solve for the the electron and I plug it in, and you get some answer. Again, there is a nice algebra here, but we are not, we do not want to delve into that, but just to show what kind of how to put down the equations. And I would like you to know that this, again, I told you, this granted Compton the Nobel Prize. And the reason was because this experiment was the first proof of the existence of photons. I mean, the existence of particles of light. Okay, good. So this is so far for conservation laws. As you remember, in Newtonian mechanics, we have two conservation laws, one for each component of the momentum and one for the energy. Now, both momentum and energy are part. We cannot distinguish between them anymore, because if you are moving to another frame of reference, what was energy in this frame of reference becomes momentum in that frame of reference, and so vice versa, like distances and time, and they are part of a form vector that have this form and have this dispersion relations. Good. Last thing we have, and this is the most not important, the most confusing thing, is force. So in Newtonian dynamics, we have force that was m times dx, d2x, dt squared, right? This was force. And the force satisfies, very importantly, the work energy theorem, which tells us that the integral of f dot dx is equals to half mv from x naught to xt t squared minus 1/2 m v naught squared, right? If we are doing work, we are changing the kinetic energy. Okay? Now the question is how to generalize it to special relativity. And there are two ways to do that. One of them is to continue, okay, there are two ways to do that. One of them is to use still the Newtonian force in the sense that it has three components, x, y, and z. It's not part of a force vector. There is no force component, right? And we have a force with three components, x, y, and z, that will be m d2 x, m d, or I can write this also as d dt of P, right? That's another definition of force. So here I will have M will be equals to dP, P will be Px, Py, Pz of this vector, right? dt, which implies that I'm taking the time derivative of M gamma times V x dy dz. Right? What is good and what is bad in this definition? What is good is that this satisfies also the work energy theorem. Right? Exactly. Okay. You're asking why? Okay, this is not a part of a four vector. It has only three components, and it will not undergo transition according to that. Right? It does not satisfy the Lorentz transformation when I'm going from one system to the other. This is the bad features of this force. Now there is another option, which is to use Minkowski force, F mu, that will be dp mu d tau. This is what you want me to do, right? This is the four vector. It undergoes from one frame of reference to the other by Lorentz transformation. We can convert it from one Lorentz transformation, from one system to the other using the Lorentz transformation, right? However, it is less transparent and it does not satisfy the work energy theory. So it requires some kind of tricky things. And since I would like to follow Griffith's book, that, one second, Griffith have decided to work with this one. So this one is good because A, it is transparent, more transparent. B, it satisfies the work energy theorem. Why it is bad? Because it's more complicated to transfer it to another coordinate system, to another frame of reference. Okay? And there is a way to use that. I'm not going to use that anymore, but you should know that there is an Minkowski force, and some books are using that, like some books are using different ones. Yeah.
So, the first equation, we can use or not use what you wrote in the book, or not? Like the transfer.
No. To transfer, you need. I will show you immediately how to transfer it to another coordinate system. It's you can't use that anymore.
Okay, so you can.
Okay. Fine. But okay, so just to understand what does it mean, suppose I have a particle, right, that is subject have a charge Q, and it is in electric field E. So the force will be QE, and I assume that now everything is in the x direction. So this equation allows me to write QE divided by m. What is this m? This is the rest mass of the particle, like the rest mass of the electron, okay, is equals to ddt of gamma times Vx. Note that gamma depends on Vx, right? But however, this equation is very simple because this is a constant. So if a constant is equal to time derivative of something, then something is equal to constant times t, right? So we know that gamma Vx will be QET over m. But what is gamma dx? Gamma Vx is Vx divided by the square root of 1 minus Vx squared over c squared, assuming no velocity in the y and the z direction. Okay? So now we want to solve for Vx as a function of t, right? So what we are doing is we can write Vx squared as q squared e squared t squared over m squared, right? Times 1 minus Vx squared over c squared. You see? I just square both sides and move the gamma to the other side. And which implies that Vx is QET over m. I'm taking this to here, divided by the square root of 1 plus q squared e squared t squared over m squared c squared. Good. Yeah. So I solved for the velocity of a particle moving under constant acceleration. And now what you find? If t is very small in comparison with QE over m, right? Then we can neglect this term because t is going to 0. Okay? And what we are going to get is, right, when t is going to 0, V is QET over m, which is a standard Newtonian answer. We have a particle under constant force, the velocity is the force times the time, divided by m. Right? Now what's happened when t goes to infinity?
T goes to 6.
We can neglect the 1. So we have QET over m divided by QET over m c squared. So we will get V is going to c, and it cannot cross the light velocity because nothing can move faster than light. Okay. So this is how one can implement the the force equation in that way. Moreover, as I said, this force satisfies the force energy relationship, the work energy relationship with respect to the relativistic energy. This is something which is nice to show, but I don't have time to do that. So the only question left is how to transfer, because this force is not a force vector. How do I transfer the three components of this force from one frame of reference to the other? And the answer is as follows. Suppose at S we have a particle moving at a velocity u, and there is some force F acts on this particle in S. How do I move it to S prime? Okay, I wanted to derive these relationships, but I have no time for that, so I will just write it. It depends on, first of all, I have to distinguish between components of F that are perpendicular to the direction of to the relative direction of motion, and the component of F that are parallel to the direction of motion. Right? So for the component of F that are perpendicular to the direction of motion, F prime, F as measured by an observer sitting here, right? F prime is F prime here, perpendicular. F perpendicular prime is F perpendicular divided by gamma times 1 minus 1 minus u x u parallel u dot v divided by c squared, where u dot v is a component of u in this direction, right? In the direction of the relative v, the relative velocity of f prime with respect to s. U is the velocity in the s frame of reference. And okay, this is a complicated expression, but it becomes simpler when u is 0, meaning that the particle on which the force acts is standing still in the s coordinate system, in which case we have f perp divided by gamma. Now what about f parallel prime? F parallel prime will be f parallel, okay, divided by 1 minus u dot v over c squared. And so that I have no time to derive this relationship. One can do that, it's not a big but now I have to subtract v over c squared, sorry, times d dt. So there is a, and also when u is 0, goes to 0, what I have here is just f parallel minus v over c squared d dt. Okay, but we are not going to use that. These are the transformation relationships. What's important? I mean, the reason why I invoke that is to end up this lecture with an example explaining how electromagnetism is indeed covariant under the Lorentz transformation. And to understand that, let's think about an infinite long wire charged. Okay. I have in S In S, I have an infinite long wire charged with a lambda coulomb per meter, okay? And I put a particle, a charged particle of charge Q here at a distance r from that wire. Question: what are the forces acting on this particle? No magnetic force. Why? Because nothing is moving. And you have only the electric force. Anyone remember what's the electric field of infinitely long wire? Right. It's you can build a Gauss thing like that, and you find that 2 pi r h is the height of this times E r is equal to lambda h divided by epsilon naught, and therefore ER is lambda divided by 2 pi r epsilon naught. Right? This is the force. No, sorry, this is the electric field, and the force is QE. So there will be a force here, which is Q lambda divided by 2 pi r epsilon naught. This is the force in the S system. Now what's happened in what a person in S prime will say. So first of all, if S prime is moving like that, right? S prime is moving like that. So this force is perpendicular or parallel? Perpendicular, okay? So it will be in S prime, this is a force in S. And in S prime, we will get Q lambda divided by 2 pi r epsilon 0 times gamma, where gamma has to do with the relative motion of the velocity of S prime with respect to S. Okay? Fine. This is one type of calculation. We have calculated the force here and move it to it. Now let's do another calculation for the same thing. We want now to calculate from the point of view of the observer here, of the blue observer, what is the charge density on this line? Remember, there is a contraction of length. So the charge remains the same charge, but if you have lambda coulombs per meter, now we have lambda coulombs per something that is smaller than 1 meter, right? The charge density, so lambda prime is lambda times gamma, right? Gamma is larger than 1. The charge, because the lengths are divided by gamma, charge density is charge divided by length, so it multiplies by gamma. So the charge density will be higher. Okay? And because the charge density is higher, what I will get here is what? Stronger force. Right? What will be the force? This length r is not changing because it's perpendicular to the direction of motion. So this implies that the force, the electric force, will be gamma times Q times lambda divided by 2 pi r epsilon. Is that good? No. Why?
Yeah, also magnetic field.
This is multiplied by gamma, and here it was subtracted by gamma. So how could it be?
Lambda is changed.
Sorry?
Lambda is changed too.
Lambda?
No.
Yes, this is a change in lambda. So this is a gamma lambda is the original. Lambda is the original one, and gamma lambda is a new, and we have all this. Yes.
But R is changed.
R.
No, r is perpendicular to the direction of motion, and lengths that are perpendicular in the direction of motion are not changing.
Yeah, also magnetic field.
Thank you very much. However, Now we have a current. What will be the current? Right? The current is lambda times gamma, which is a current density in S prime, times V. Right? This will be the current. And what is a magnetic field generated by a current in that direction? Right? If you remember, the magnetic field is mu naught I divided by 2 pi r, right? Ampere's law, right? Which is, this is I in the, again, so we have mu naught times gamma lambda V divided by 2 pi r. This is the magnetic field, right? And since everything from the point of view of this observer, everything is moving to here, so the magnetic field here will go out of the black hole, right? And now, how much force it will apply on this particle? This particle is also moving in the same velocity, right? So we have Q V cross B will be Q times V times B, which is mu naught gamma lambda V divided by 2 pi r, right? What will be the direction of the force? The magnetic field here is moving out of the blackboard, right? And the velocity is to here, so the direction of the magnetic force is this way, right? So this will be the magnetic force in the S prime, right? F magnetic prime in the prime system, and these forces do not exist in the S system because in the S system nothing is moving. So all in all, we have F electric, which is this, and F magnetic, which is what? Q times lambda times gamma times V squared mu naught divided by 2 pi r. So the total force in S prime system will be this minus that. Okay? So the total force in prime system will be Q, what is common to all these equations? Gamma Q lambda divided by 2 pi r. Let's put the epsilon naught also here, right? Times 1 minus Z, so gamma, Q, lambda, and 2 pi r were also, so I have V0 squared times mu naught times epsilon naught. This epsilon naught, we cancel this one. Oh. But what is mu naught epsilon naught? 1 over c squared. So what we got here is gamma Q lambda over 2 pi r epsilon naught times 1 minus v squared over c squared. Now this is 1 over gamma squared. So we've gotten Q lambda over gamma 2 pi r epsilon naught in agreement with that. Right? So this shows you that indeed the laws of electromagnetism are covariant between the two systems. It's the same laws of electromagnetism, but the force that was purely electric force in one system is becoming a combination of magnetic and electric in the same way that time is now a combination of lengths and times in the other system, and so on and so forth. This was the first taste of what you're going to see during this course, and the rest is left to Eli Barkai. Good luck. Thank you very much.